Hello, so it's Mesomachi here, and together with a fellow instructor at Special Maths Academy, Pius, we will be discussing the solutions to the just concluded 2024 Special Maths Contest, the first round. Please share this video, like, comment, and don't forget to subscribe. We need those subscribers. Enjoy the video.
So once
Okay,
again,
Ms. Mache.
we've convened to continue our discussion about the problems from the just concluded Special Maths Contest 2024.
Right.
And we're looking at number 24. So let's dive right into it.
Very good. Yeah, so this is the second to the last problem. So being quite at the bottom of the list, it means it must be relatively difficult, right?
Yeah,
so
exactly.
let's see how it goes. This is a number theory problem. Obviously, we're dealing with prime numbers, with GCD, and also with divisibility. All right. Okay, so
can you define what GCD is? Like, what exactly is GCD?
All right. Okay, so to keep it simple, I'll just define it for two integers. So typically we're working with positive integers, but it doesn't have to be positive integers. So GCD is going to be a positive integer. So it's the greatest possible positive integer such that C is a factor of both A and B. So when we say GCD, this is a representation for GCD. So this is short form for greatest. This is common. Then here we have divisor or factor. So others may be familiar with this as HCF, which is highest common factor. It's essentially the same thing. Yeah.
Yeah. Okay.
So yeah. So it needs to be an integer first of all. It needs to divide A. It needs to divide B. And then among all those possibilities, we pick the greatest of them. That's it. So here we have also prime numbers. I think we all familiar with prime numbers, I guess.
I want to believe so.
Yeah, I would like to assume. Okay.
if you aren't really familiar with prime numbers, you probably should watch, some videos discussing prime numbers before coming to like this video. Okay.
Yeah. So for this problem, this will be assumed to be a bit more on the basic side, based on the level of difficulty of the problem. All right. Now, the first condition we have to figure out what this P and Q, what they could be, right? So actually, you're interested in Q. Maybe we may not necessarily be able to get P, not necessarily. But we're interested in Q. So the first condition, let's see what we can figure out from here. Let's call this greatest common divisor, this GCD, let's call it C. So we're saying that the number that divides P minus 1 and also divides, so let me demarcate this, excuse me. So the number, what just happened? Anyway,
the line ran away.
Yeah, I got too scared. All right,
scared of the
so
problem.
we have Q minus 1. So if you have like a positive integer dividing both of these, and we pick the greatest of them, where we want that to also divide 12. So this means that we can actually tell the possibilities for this so-called greatest common divisor. It has to be a factor of 12 because this needs to be true. So the options here would be 1, 2, 3, and then there are cofactors 4, 6, 12.
Yeah.
These are the options. So this means at this level, we can say we have 6 cases where the GCD is 1, is 2, 3, 4, and so on. Now, for example, if the GCD is 6, it means that we need 6 to divide P minus 1, 6 divide Q minus 1. But just this, writing like this will not tell us that the GCD is naturally 6. just means 6 divides the GCD.
Yeah.
So writing it this way may not be very good at this stage. So we have to revisit this based on whatever information we get next.
Yeah.
Now let's go to the main part, I think.
The more intimidating looking part.
Yeah, it looks nice, but it carries a lot of information.
Yeah, I think we can say that.
So here we have this is a divisibility sign. It means that Q is a factor of this integer here. We have 2 raised by p minus 1, then minus 1. So if you have something like this, typically we tend to write this in terms of modular arithmetic, especially if we're dealing with prime numbers. It's most useful to write this in modular arithmetic. So this would be the same as saying this is congruent to 0 modulo Q, right? And then now we can perform the arithmetic as though this were like an equality sign in terms of additions and subtractions and multiplications. Divisions, we will have to be a bit more careful with that. So we have this. Now at this stage, we can talk about something else that should come to mind if you have like powers, trying to evaluate powers in a mode. Usually there's going to be an order where the powers, when you keep multiplying, taking like a geometric series. So let's say you have 1, and then you have times 2, and so on. If you take it in a fixed mode, since the mode is fixed, eventually you end up getting the same remainder. And actually, there's a point where you get back to having remainder 1.
Yeah. And once you reach remainder 1, it becomes cyclic.
Yeah, it just becomes exactly. So that becomes like a periodic order.
Yeah, periodic order.
And if we can find out that order, usually it helps us to solve the problem. So to solve this problem, you need to be aware of that principle, that there's an order. So there exists some A, which I will call the order of 2 in mode Q. This working mode Q. So what does this mean? This means that 2 raised power A will just have the same remainder as 1. And after this, we'll just be going in circles. Because now if you multiply by 2, you just get 2 again. Until you get to A, it becomes 1 again. So this will be the first time. So this has to be the least.
Yeah.
The first time this happens. And after every A value, so you have 2 raised power A, this becomes 1. If you have another 2 raised power A multiplied to this, it just becomes another 1 again. So this means that those values, one can actually show that those that if you have 2 raised power x congruent to 1 mod q, then x will have to be a multiple of a. Because we're going in circles. So just imagine you start from a point here. After a steps, you get back to 1. This is the first time you get into 1. So the other values you visit here, they are all different from 1. So each time you take a steps, you get to 1. A steps, you get to 1. So if there's any value that gives you 1, it must be based on those complete circles. So it must be a multiple of a. So that's the logic here. So with this now, we can analyze the problem a bit better. So on one hand, we have what we got from the question. So p minus 1 is such a value that gives 1. So whatever a is, we don't know what a really is per se, because it depends on q. So, but whatever it is, we know that p minus 1 has to be a multiple of that a. In other words, a is a divisor of p minus 1. So this has to be. And if a is the divisor of p minus 1, this will also hold. So this actually captures that information completely. Then now, based on the structure of the question, it's going to be logical to also consider Fermat's little theorem. So this, you can only consider this if you're familiar with it. If you're not familiar with this, you probably will not think about it. Right? So here, we want to use Fermat's Little.
But do you think this theorem is little?
Maybe for this guy, I think it's maybe for him is like it's like, no, what, just write a little something here. So but definitely not little, right? It's a theorem.
It's not a
so
little
obviously
guy.
it's not little. It's a theorem. It cannot be little, right?
Or maybe
but I think it's just from Fermat's perspective. Maybe it's like
maybe
it's a side quest. Yeah. So and it's maybe also little in the sense of like the statement is also very straightforward, I think.
Yeah, the statement
and
is
the proof also not too complicated.
Yeah,
if you know what to do.
Complicated. Yeah.
Yeah. So this theorem, just to make sure we are all on the same page. So if you have some number as like the base, so we have that this is going to be congruent to 1 mod p, given that p is prime and b and p have no common divisor. So the GCD is 1. Since p is a prime, it means that we can only have that p doesn't divide. Yeah, it's only one on p. So and if it's p, that's only when p divides b. So it's the other case where p doesn't divide b. So yeah. So basically, so long as b is not congruent to 0 mod p, so that this is like kind of irrelevant. So long as it's not some trivial value, then we can always reduce this to 1. Always. So that's the idea. So meaning that we'll now need to make sure that condition really holds. So in our case, this is only true if Q2 doesn't reduce to 0 mod Q. So that means Q doesn't divide 2. So here we need to use this. We'll need Q to not be equal to 2. Now, suppose Q is equal to 2, we'll take that as a special case. Yeah. So for now, we'll safely assume that Q is not 2. Then we can apply this theorem. So based on that, now what we get is something similar to this result, which would be that here instead of p minus 1, now the number we have there given the same result is q minus 1. So that means a is also a divisor of q minus 1. And this probably should look familiar at this point because we have a C from the beginning. We have C having such a similar structure, right? So that means there should be a connection somewhere. So let's see how we can draw that connection. So here we have that A is a common divisor of P minus 1 and Q minus 1. And now, if we have A common divisor of P minus 1, Q minus 1, there's a result that tells us that it must divide the GCD also. So we'll just use that here. So this will be equal to, so this follows from Bezel's lemma. This is just our C, which we knew divided 12. So why is this helpful? So this means that A divides 12. Why is this helpful? It means that the possibilities for A, which we never knew from the beginning, now we can narrow it down to just those 6 possibilities once again. So A is not necessarily equal to C, right? A is not necessarily equal to C, but it satisfies similar conditions with C.
Can you recall what A is? Can you remind the viewers what is A?
So A is the smallest value that gives us 1 as remainder mod Q. So now there are possibilities we have narrowed down. So this is where it's very important to have just few possibilities. So now we can try to check a bit more and narrow things down to Q, hopefully. Sorry, this is 6, 12. Okay, so for each of these, we'll now have to consider them as different cases. So each of them is going to also give us a narrow options for Q. Because what this means is that Q will need to divide this if we simplify it, which should be some value. So we can check the factors. We just need a prime factor. So when A equal to 1, this means that Q have to divide this. It doesn't make sense. So
contradiction immediately.
at least one. Actually, it's good to have contradictions so that we can move on. Otherwise, we may have to check a bit more things. So let's check 2 now. Mind you, we are considering that Q is not equal to 2, okay? That's the assumption here. So here we have A equal to 2, then Q will have to divide 2 raised power A raised to power 2 minus 1. This is 3. So Q will have to be equal to 3. If there's such a solution, it will have to be 3. So now the question is, does this 3 actually work? Can we have like a solution for 3? Because we need a prime P that we should be able to match with this Q to satisfy those conditions. So what would that look like? We need P minus 1 with 3 minus 1, which is 2. We need this GCD to divide 12. This part, you can see that it's going to be obvious, right? Because this already divides 12.
12, yeah. So the GCD is here. Yeah, the GCD divides 2.
Yeah. So many of them will have this kind of scenario actually. So what we do need to worry about is the other one. But for the other one, it's also not a problem because now we have P, we need P to divide 2 raised to about 2. Am I having this right? Hold on. And make sure I'm having the right. Okay, it's the other way around. Q. Sorry. So we need Q to divide 2 raised to power P minus 1. So here we need 3 to divide 2 raised to power P minus 1. So what this means is simply we want. So it doesn't matter which value of P we have. This first one is always true, right? So we just need to see if there's a value of P where this can be true.
Yeah.
And for this to be true, if we already know like one of those circles, we can just take a multiple and go along those lines. So if we can make sure P minus 1 is multiple of the circle that this forms, which is 2, A equal to 2. If P is a multiple of 2, any P that satisfies this would already be a possible solution. So we just need this to be even, and which will be for any prime. So P can actually be 3, for instance. So we don't need to. So here we see that actually there are definitely many values for P.
Yeah.
Yeah. But all these are grouped under a single value for Q. So we have one value for Q that works. So the rest are just going to be similar. So maybe we can go a bit faster. Very similar principles. So here we have to this is the order. So 3, this is 7. So Q has to be 7. And now we need to confirm. So we compare this with 6, which already divides 12. So once again, this is good. Then we need 7 to divide 2 raised to power P minus 1. So we can still use this order. So we just need P minus 1 to be a multiple of 3. So we can pick P equal to 7 actually. Do they have to be distinct? So it depends on if they have to be distinct or not. Okay, they are distinct. So maybe we can just go with different primes. So yeah, we'll change this to 5. This we can go with say 13. Okay. But actually there are infinitely many values, so it's not really such a big deal. So this also works. Is 4. So this is 4. Q divides. Remember, this A should be the order.
Yeah.
So meaning that it has to be the smallest. So I think that will come in handy here. This can be factorized. Well, I mean, we can just simplify and factorize, but this is 3 times 5. So why I stress that is that even though it seems like Q can be 3 and 5, although we already dealt with 3, but strictly speaking, under this case, Q cannot be 3.
So why
because
can't
now
Q be 3?
if Q is 3, then we'll have a smaller order than what we claim.
So
suppose Q is.
What's the order for
So here,
for 3.
3. That would, because that comes directly from this expression.
Okay.
So this is already the order.
Yeah.
At least it can only be smaller than this. So 4 will not qualify for the order. So we just keep this in mind. Either way, we already have Q equal to 3 before, so it's not going to even give a new value. So, but just to be clear. So now we have 5 as a possibility. Now let's check the here. Once again, this is smooth. This again, we expect infinitely many values. We just need to find one that works. So the order here is 4. So we need 4 to divide p minus 1. So once again, we can actually pick p equal to 13. Case, I think we have 2 more cases. Case,
yeah. So 6 and then 12.
Right.
So case 5,
6.
A equals 6.
So based on what happened here before, we might have multiple possibilities on the surface. But so this is just 63, by the way. So this is 3 squared times 7. But there's no point of continuing this because we already have 3 and 7. So this is just fine. Nothing new.
Yeah.
For sure. New. Whether they actually have this order or not. In fact, from the previous question, we already know they don't have this order, right? Because they already fall under this other category.
Yeah,
so
because order is
actually
the
no solutions here. Yeah. So now we can move on to
case 6.
6. So this divide 2 to the power 12. So now this number is getting on the bigger side. So we just use our difference of 2 squares to write this as this. This part we already have here 63. This is 65. So most of these are already repeated. The only thing we have new here is perhaps
13. I think 13 is new. Yeah. Q equals
yeah, 13 is new. So now we do need to check 13 to make sure if it's a solution or not. So Q minus 1 here is 12. So this once again is very good. No problem here. So we need the 13 to divide this. And the order for 13. So in this case, the order for 13 is not necessarily 12, right?
Yeah.
It's not necessarily 12. Is it 12? What is the order?
Wait a
I'm not
minute.
sure.
The order has to divide 12, but let's see.
So the order, yeah, we can be sure it's 12 actually. Yeah, if it were not 12, it will be one of the previous cases.
Yeah.
But since we've not encountered it so far,
so if it was 6, for instance,
yeah, would have seen it under this.
Yeah.
So actually, it's safe to not even worry about that aspect based on the fact we're considering all the factors of 12.
Yeah.
Yeah. So that in that case, it's safe in terms of the order. So it's indeed part of this case. Then now we just need to find like a P that satisfies this, any P, and then Q would be qualified. So we need the order, which is now 12, to divide P minus 1. But P is not 13, so we need a different prime. So we can have we have 25, we have 37, so we can have P equal to 37. So this means this also qualifies. Yeah, so that will bring us to the end of this. So that gives us this primes P equal to. Okay, so that's not the end really. We need to consider 2, right?
Yeah, the case for 2.
Yeah, sorry about that. Okay, so let's look at 2. So 2 is actually a straightforward case. If suppose Q is equal to 2.
Can you just write down the conditions for the problem again?
Yeah, I'm going to do that now. So we need this to divide 12. We need this to divide. So the issue here is that this number here is always going to be even if P here is 2. This is even.
Yes.
So altogether, this is just odd. So Q has to be an odd prime, actually.
Yeah.
So maybe we could have done this from the beginning, I guess. So, but basically,
so by
this
parity
doesn't get
arguments,
anything. Yeah, by
arguments on the
parity.
parity. Yeah.
But in terms of this aspect, it's also fine like the rest of them. This will just be 1, so whatever works here.
Yeah.
Yeah, so we are still left with 4, which is 3, 5, 7, 13. So definitely there are finitely many of them. They have to be. And then let's see the options. So we have B.
Yeah. That's an interesting problem. Short-worded, but yeah, I would say it deserves the position of 24, 25. I mean, it's sufficiently difficult. Okay, so
Definitely.
I don't really have any comments about this problem. I think it's an attractive problem in the sense that it calls on applications of different concepts from number theory. So you have Fermat's little theorem, which is not really little, and then you have things like modular arithmetic, order. So
Order.
it's
We
an
have
interesting
the GCD properties of GCD.
So do you think there's a way maybe we could apply periodic values? Just throwing that out there.
No, not really.
Okay.
This question doesn't require that that kind of knowledge. So even if you apply it, you still like to apply periodic evaluation. There are some groundwork you need to do, and that will bring you back to what we've done, basically. So it's like you taking it a step further than what we've done. Then maybe you can apply things like periodic evaluation. But at the level of this problem, it's not needed yet.
So what really made this problem special? What makes it special between 12 and 2? So we have like P minus 1 and the GCD of P minus 1 and Q minus 1 must divide 12. And then we have 2 appearing somewhere there, like Q must divide 2 to the power of P minus 1.
Okay, for the choices.
Yeah, so what makes this problem special?
It's not special, actually. But
so can we replace 12 with like a random number?
Yep, with anything. But
and we can replace 2.
It only makes it more difficult if the numbers get more complicated. You have to bring the numbers under control. So 2 is like the numbers that's like the lowest base we can have. That is still reasonable. Excuse me. So you can use 3. 3 is not too bad also. From 5 is already getting a bit too big, so you may need to consider.
If we like increase the base,
some things will change. So let me show you
it would be better to reduce 12 or something.
So if you increase the base, these numbers we're getting here, 3, 7, 63, and those things, they become quite big. Like even after factorization, you still need to work on them, especially if you come, like you said, if you didn't change 12 also, and we had to get to this point of 12, this is where you really feel it the most. This is where it contains like all the factorization. So you have to. So imagine getting like maybe 3 raised to power 12 or 5 raised to power 12. 5 doesn't look like a big number, but this is now no longer friendly. Yeah.
I think
so. It can be done, but it will take too much power.
Yeah. So something else I can say is that if we have something like b to the power of, let's say, a to the power of b times c minus 1. So a, b, c are integers. So maybe you can scroll down and write what I'm saying.
Let me. Okay, something new. Okay, let me go.
Just an idea that someone can take away from this. So if you have something like a to the power of b times c minus 1. So a, b, c are integers. So a to the power of like b times c is the power.
A.
Yeah. So to the power of b times c. Yeah. Then minus 1.
Okay.
Down. Yeah.
Okay.
So b times c is just the power. So a, b, c are integers. So what we can say is that a to the power of c minus 1 divides this, and a to the power of b minus 1 divides this. I think that's a good idea to have for a problem like this. What do you think?
Sorry, I think I missed something. Come again. So if you have this, so what's like the
So a to the power of b minus 1. And then a to the power of c minus 1.
Oh.
No,
Okay,
not
sorry.
yeah. Just b to the power. Yeah.
I got it.
And then a to the power of c minus 1. So these two things divide that guy on the left. So I think
yes.
This is a nice idea to have for problems like this.
Yeah. So actually, some of these things we said about order can be like one can kind of avoid using the word order if you use something similar to this. Like there's a result that talks about the GCD of these two. So just now that you mentioned this is actually equal to the GCD of their powers, because both of them, like the division kind of works like almost in the power sense. Like this divides this. So if they both, like if you have something that divides both of them, actually turns out to be something similar in that direction. So if one already knows this result, for example, it will kind of save a bit of some of the things we did. But knowing that, it's like you already know how to approach the problem too, probably if you know that result.
Yeah, probably.
So it should just be more like it doesn't ignore the other things we did. Just in terms of order, you can now ignore the other part. So this will simply be excuse me, 2 raised to power. So maybe you can also have an idea of how the problem came about.
But yeah, this is an interesting.
So this is the
result.
GCD now. Now we've limited this value to be like some possibilities.
Yeah.
Yeah. So that has limited this one also. And then yeah, so now if Q is like the common guy for both of these, then it has to also kind of go into this kind of thing. So this one naturally is a multiple of Q. So this would be like the new stuff. So basically you just want to talk about like a factor of this that divides both of these, but now we picked like a natural factor of 1 so that we don't have too many conditions in some sense. So it's now hidden as to what is actually going on.
Okay.
Yeah.
So let's see how the participants fared in this problem. I already have my plots ready.
All right.
Yeah.
Nice. Let's see how this goes.
Okay, so you can see my screen. So an interesting take from this, when I was analyzing the statistics of the submissions, this is the only problem where we have a bimodal distribution. So option A and option D had the most, they're equal in terms of like the number of participants that selected them, and it's the only problem that had this
wow
feature.
Interesting. Yeah, I think it's maybe a coincidence.
Yeah, probably. Well, yeah, and also this problem had the distribution of the options had the highest entropy. So I think this was the problem where the option selection like scattered the participants the most. So you have the highest.
So probably a lot of guesswork.
It's almost evenly distributed. Yeah, probably a lot of guesswork went into this.
Yeah, and not just guesswork, but also an even number of like is the options are so unrelatable that one has no idea which options could probably be like a good guess.
Yeah.
So it's so random for it to have like such a leveled like high entropy. It means that the options, none of them like stood out in any way. They all look like something that could be possible for some reason.
Yeah.
Maybe it could be infinite for some reason. Like it's not strange for it to be infinite. Maybe the numbers are huge and then you're just supposed to not really get them all, you're not sure. Or you found 3 and then you don't know if there are more. Like this kind of stuff. So, but if someone found 4 options, then you can now eliminate A. But for you to find 4, you have to go all the way to 13, which probably one will not do for an exam like this where you don't have much time.
Yeah.
To just be checking options, because even if you find 4, you're not sure if there could be one more. So I think maybe because of that, most likely many people probably guessed. Yeah.
So yeah, it's interesting to see how, sometimes these things play out, but it was an interesting problem. Okay, so that'll be it for this video. Do you have any other comments before we end the session?
Okay, I would just say personally, this is one of my favorite questions.
your favorite, one of the favorite from the contest.
From this competition. Yeah.
Okay, so
all right. Thanks.
Yeah, viewers should stay tuned for more video solutions. Goodbye, everyone.
Yeah. Goodbye.